All right, here's a proof of Theorem 11. Theorem 11 is one I like to call grow a perpendicular. It has given line AB and a point on it, C. And the idea is to grow a perpendicular from C up to this point F that we're going to determine up here, okay, with only using compass and straight edge. Again, you can use, if all you want to do is just make a perpendicular, you don't care about it being compass and straight edge, just take a right angle, like on a piece of paper, and line it up so that the bottom edge goes along CB, and then just draw along this edge up here, and you'll have a perpendicular. That's the easy way to get this. That's the way an architect would do it. They would use something called a square, okay? And they would just use a manufactured right angle. And most straight edges have right angles on them like this, so you can just go like that. But of course, that's introducing a new tool. We're only allowed in Euclid to use compass and straight edge. Okay? So, let's start. So here's the construction. It's given that we have a line AB with C on it. C can be anywhere on it. Now, in Euclid's drawing, C is like the midpoint of AB. Does C have to be the midpoint of AB for this to work? No, it does not. So I purposely put it kind of off-center so that you wouldn't think that you can use A and B, because A and B are totally useless at this point. Okay? Instead, I'm going to pick a point D on AC. That's my first step. Choose D at random on AC. That should feel familiar to you. You've done this kind of thing before. And what are we going to do? Cut off CB at E so that CD equals CE. Okay? And so that's easily done with a compass. You just open the compass to be CD long. There we go. And just swing it over here. Boom, there's E. All right. So what theorem is that? Class?
Theorem 3.
That's theorem 3. Cut off a longer line to equal a shorter one. All right. And then step 2 is we're going to do a theorem 1. On DE, draw or construct EQ triangle, equilateral triangle, DEF. Oh, I called it EDF. Doesn't matter. That's theorem 1. But specify that it's drawn on DE, obviously. I guess you don't have to say that since the E and the D are already in the name of the triangle. And of course, making an equilateral triangle is super easy. All you need is the intersection of two circles. So I'm just going to do the intersection only, do the short version, and there is point F up there. All right? And it's part of the construction to draw the lines, so I don't need to say draw FD and draw FE because that's part of theorem 1. We already said in theorem 1 that we're going to use postulate 1 to draw that, so we don't have to repeat it here. So now the only step left is to join the points F and C by postulate 1. All right, I say that FC will be guaranteed to be perpendicular to AB. As you know, Euclid's definition of perpendicular is a line standing on another line that makes the adjacent angles equal to one another. So if angle 1 equals angle 2, then the lines are perpendicular. This is perpendicular is such a long word. I love that we have this symbol that means perpendicular. So I don't have to write out perpendicular. It's a horrible long word. All right. So all I really have to do is prove that angle 1 is equal to angle 2. And obviously, how are we going to prove that? We're going to show that there's a few triangles that are congruent here. The two triangles obviously are going to be FCD and FCE. So it's given that we have just done this construction above, and we got to prove that, oh, I forgot to say what to construct up here. Sorry about that, missed that. Our goal is to construct FC perpendicular to AB. So that's what we have to do. We have to prove that what we set out to do was the actual thing that was done. All right, step 1. We have these two triangles. We need to prove them congruent. Okay, we could either use the SSS or the SAS. Really doesn't matter. We could actually do both of them in this one because there's a way to do it with the SAS. But I'm going to do it the way Euclid does it, which is the SSS. He starts out by saying, since DC is equal to CE, and we did that back here, step 1 of the construction. That was based on Theorem 3. And then we also know FD is equal to FE. I wrote them in the opposite order that I said them. That's okay. And that's because of the definition of EQ triangle. And we also know FC is equal to itself. And that's because of axiom 4, or reflexive. Click, click, click. I just heard the locker open. Triangle FCD is congruent to triangle FCE by the SSS. And again, I can point out that the first three, the order does not matter at all on what order the first 3 steps come in, but you may not do step 4 until these 3 steps have been declared. Okay, so now we reach into the locker, we take out the precious part, angle 1 and angle 2, and we say that they are equal by CPCTC, and hence that proves, as I said before, that FC is perpendicular to AB by the definition of perpendicular, which is a line standing on another line, making the two adjacent angles equal to one another. QEF, quod erat faciendum, which was the thing we were supposed to make or do. All right, and we have made line FC perpendicular to AB. So there we are done. Quod erat faciendum.